Hey everybody and welcome back. This video is going to be all about traversals and searches through linked lists. We're going to talk about walking through linked lists using just the classic while loop and making sure that we do it safely, which means handling situations like empty lists or reaching the end of it. We also really want to make sure that we avoid things like infinite loops. You can kind of think of a linked list like a treasure hunt or a scavenger hunt where each node in the list gives you a clue to where to find the next one. And we're going to follow that trail today nice and safely. In order to get started, we do need to make a node class and a basic list. Class node, a reminder, use private variables with getters. Let's go ahead and write it as a do what I say, not what I do example one more time. I will add this time my constructor. This dot data is equal to a new, is equal to data, and next can just be null. And then let's also add a toString just to make it a little bit nicer for our prints. Public string toString. And we can just return data. There we go. I'm going to close up this node class just to get it out of the way. If you're coding along, pause now so that you can go ahead and copy it out. Because once I close it, it's closed. We're not going to actually touch the node class again. Okay, so let's start by adding a bunch of nodes to our to a list. We're going to start with a node top A, a node B, a node C, and a node D. Whoops. And let's link these together. A is going to be connected to B, B is going to be connected to C, C is going to be connected to D. The last thing I want to do is make a top or a head node so that I can just sort of focus on that from now on. So this should have connected 1 to 2. This should have connected 2 to 3. This should have connected 3 to 4. And this made top equal to 1 to 2, which was connected to 3, which was connected to 4, which was of course connected to null. At each point in time, you can kind of imagine that this is what it looked like. Okay, so in order to visit every single node, we want to make a temporary pointer that we often call cur for current. It's going to start at our top node and it's going to move forward with each step. A reminder, we're making that extra current variable, that temporary helper, because we do not want to lose our top reference. It's kind of, sometimes I explain it like in video games or like in a sci-fi movie when somebody has to go through a portal and so they like tie a string around their wrist or around their waist so that like people on the other side of the portal don't lose them. If we let go of that, if we cut that top, if we get rid of that portal string, the other person is lost to time. That's what we're talking about here. If we cut off the head, we lose the rest of our list. So keeping that in mind, when we try to do things here, we don't want to lose our top. Let's go ahead and make a method here that will actually just print out our whole list. Print list. And it's going to take in that top node. Let's just call it, let's just call it top. So if we're going to print out our whole list, print list, we pass in top. Like I said, the first thing we want to do is we want to make that cur variable equal to top so that they're pointing at the exact same piece of data. This is our tether to walking through. This is like asking somebody to go through the portal and help the person on the other side. The person who is the tether in the real world doesn't walk through the portal. We lose everything. Instead, we tie somebody else on, in this case, cur, and let them walk along the rope. And like I said, we've got this basic while loop that we use for all of our traversals. While our current is not at the end of the list, what do we want to do? We want to print our data, print, and find the next person along the portal rope. Now, unfortunately, Kerr is a red shirt, which if you know Star Trek, you'll know that this means they are dispensable. They are gonna die. We're not actually caring if Kerr gets lost, which is really sad if you're using the portal example, but fine when we're just talking about memory. So the first thing we're gonna do is we are going to print out that data. And since we do have a toString, I can just say, whoops, Kerr. And then Kerr's job is to find the next person along the portal rope. So Kerr needs to walk to the next person in the list. And that is all there is to it. The loop is basically the DNA of all linked list operations. We start at the head, we stop at null, and we just keep moving forward one next at a time. Let's run this so we can see exactly what's happening. Oh yeah, whoops. I guess I am opening this one more time because this is an int. And I can just turn it into a string in kind of a hacky way like that. Concatenate a string on and it will technically work. All right, let's go ahead and run it. And there we go. We can see that we're printing out 1, 2, 3, 4, just as we expected, starting at 1 and just going to .next each time. You'll notice that we don't print out null, and that is because once Kerr equals Kerr.next and Kerr.next after 4 was null, we came back to the top of our while loop. While Kerr does not equal null, well, it does equal null, so now our code stops. So we just don't ever actually end up printing out that keyword null. But that's okay. Most of the time, we don't really want that printing out anyway. I'm going to add this extra new line just to move that % down. There we go. Now that we understand the basic linked list and the basic loop, let's go ahead and create an index method. Let's see if we can find our index. Public static int index of. We're going to pass in our list and the value that we're looking for. So we're going to go looking for this target value. And just like Java's built-in linked list classes, Java's built-in index of methods, index of returns the index, val is found at, or -1 if not found. All right, we're really starting to get into some problem solving here. So we should probably be keeping track of that found index. And just like any time we've written an index of in the past, we can actually start it off at -1. We then are going to loop through the list. If the data at the position is the value, then stop. Else, go to the next element. We want to keep looping until we find the element or reach the end. Awesome. Let's get this all set up. So we understand that we're going to need some kind of keeping track of a found index. We also understand that we're going to need that temporary Kerr variable, as I previously mentioned, to start us out. We always want to make sure we do that. Now, if we're going to loop through our list, we're going to try to find the element or reach the end. So while our found index is less than 0 and our Kerr is not null, we want to loop. At the end of this, we're going to return our found index. If the data is at this position, so if Kerr.data is indeed val, we found the indexed position. Oh, what should this value be? Since we don't actually keep track of position, we're going to have to. It starts at 0. So we can say if we found it in the first position, it's now going to be 0. What do we do if we didn't find it? We're going to go to the next element. And how do we go to the next element? Well, we need to increase our counter since that's keeping track of our index. And we can do that same formulaic cur is equal to cur.next. And this will allow us to loop through our list until we reach the end. And that's all there is to it. Let's go ahead and test it out. So we can still print out our list. That's fine. But let's also now do an index of call. Let's first go looking for the value 1. Top and 1. And our expectation is going to be to find 1 at position 0. This should print out a 0. Just make this a little bit bigger. There it is. We found value 1 at position 0. Let's just rewrite this. Val 1 at position 0. Let's do one more, and let's hope for it working in the other scenario. Where are we going to find the value 10? Well, if we look at our list, it's not in there. This should return -1 because we're not going to find it. And I forgot to change this to 10. Got to actually update that value that's getting passed in if I want this to work. We move that out of the way, make it a little cleaner. And there we go. We have our list printing out as we expect. We find value 1 in position 0. And we went through the whole list without finding value 10. And so our position returned as -1. What happens if we try to do this with an empty list? A list is considered empty if the top is null. There's nothing in the list yet. What would happen if we tried to run this over an empty list? Well, let's go take a look at our code and actually see. We come into index of, we get top gets set to cur, found index is less than 0. Is cur not equal to null? No, cur is null, right? Because cur starts as the top variable and that top is just referencing null, in which case we don't go into the loop and we just return our found index of -1 because an empty list is still technically a list. It's just empty. So we did not find that value in it at all. A pretty common bug that often comes up with people using linked lists for the first time is creating your loop like this and then forgetting to do something like this. We forget to move cur along that rope. In that scenario, if we're not printing as we go in our debugging, our code hangs. We end up with an infinite loop. And it's sometimes tricky to see that that's what just happened because it looks like so far it worked. But actually, in reality, it's not. So whenever you have something like this happening, so a really good idea when you're writing linked list code is to add in those print statements as you go, just to sort of help avoid those situations. You can really print out anything. Inside while loop with position, and then I just print out the value of position since that is something that's changing each and every time. Watch what happens. Oops, I forgot to go cd desktop, compile. Now I know I'm stuck in an infinite loop because I see my values going up. It's kind of slow looking, but we still see it happening every single time. The way that like the console prints stuff out is it's going to keep, like it buffers and then flushes it to the console, which is why we're seeing these jump in values when things get infinite. But we can see it's never ending and I can go, oh, whoops, something really weird happened. I look at my else and I see that I didn't actually do what I said I was going to do. Go to the next element. That was missing, right? So we can actually see that that's happening here. Let's go ahead and just close that panel off and reopen it fresh so that we don't have that problem anymore. So it's really important that we understand some of the common pitfalls, but also know how to debug them. We'll put that back in and make sure that we're leaving our code in a state that's working appropriately. So Traversal basically means use your current variable, this one, right? Your temp cur variable, stop at null, and make sure that we advance at every single step. This really is the foundation of everything with linked lists. We're talking about searching, counting, deleting, everything. I will leave you with a mini challenge if you're looking to practice. Try taking this code and then adding another method called the last index of, and see if you can return the last index where a value appears. It's a really good little challenge and a great way to practice your linked list skills. In our next video, we're going to talk about proper insertions into a linked list instead of what we've been doing thus far. So far, I've been doing a lot of manual linking, and that's not the smartest way to do this. So in the next video, we will be looking at better ways to get data into our list. Thanks, everyone, and I'll see you there.